So today we're going to go through the June 2018 Synthesis and Analytical Techniques paper. So we start with the multiple choice. Nice and easy one to start with. So which one is used as a standard for NMR, chemical shifts? You'll know it as probably TMS, which is tetramethylsilane, and so the answer for that is A. Which compound here is a secondary amide? So secondary amide, you're looking for the group where you have a carbon-oxygen double bond, then a nitrogen, then you've just got one carbon coming off and an H like so. So the answer will be C. Remember, you've got to have that amide group, that amide bond there, that's the important one, with one carbon coming off. D would be a tertiary amide, and these two aren't amides at all because they haven't got the correct linkage here. So we're looking at what compound will now not react with a nucleophile. So nucleophile is something that's going to be attracted to positive charge. So this is obviously an aldehyde group, so you've got a delta plus carbon, which would attract nucleophiles. However, for B, that is going to be an alkene. An alkene will obviously attract electrophiles, so the answer is B. Which structure represents an alicyclic compound? So you're looking for a molecule here which has a ring in it but does not have any aromatic character at all. So obviously A and B both and C are all aromatic, so your answer is C. So for question 5, we're looking for a molecule which is not planar. If you just have a quick look down, you will see that the answer is going to be B, which is ethane. Ethane, obviously the shape around those carbon atoms are going to be tetrahedral, so the answer to 5 is B. What is the number of peaks in that spectrum? So let's draw them out. So if we count out the different types of hydrogen, these two here are going to be the same. Those two are the same. And then you've got the hydrogen there and the hydrogen there, which are different. So you're looking at 4 peaks, so the answer is B. Which of these reactions has the lowest atom economy? So your atom economy is given the molar mass of the molecules you want over the molar mass of all your products. You can do the quick calculation, but if you have a look, you've got bromine there, hydrogen bromide, so the bromine has got a high molar mass. Hydrogen bromide has a high molar mass because bromine's got a high relative atomic mass. You don't want the hydrogen bromide, and therefore the answer is going to be C. So you need to know the equations for the breakdown of ozone by NO radicals. If you know that, you've got to know those two equations. The answer for 8 is a D. And then you are producing an NO free radical there. So which molecule could have produced the IR spectrum? Well, if you have a look through, you have got an OH group there, and you also have a CN group coming in there, so your answer is going to be B. So what do you need to add to benzene to make phenol ethanone? So this is going to be an acylation reaction. So you're looking at adding this molecule here, so your answer is going to be C. How many straight chain structural isomers of C7H15 contain a chiral carbon? So there we go. So we will have a chiral carbon if my Cl goes there. You will also have a chiral carbon if my Cl goes there. But if you put your Cl there or there, you will not have a chiral carbon, and therefore the answer is B. So your highest intensity peak here is at 43. So it has to add up to 43, but it also has to make chemical sense. You can't start rearranging a molecule, so the answer there is going to be C. Number 13, which statements supports the delocalized molecule for the structure of benzene? So that one does. The enthalpy change of hydrogenation of benzene is less exothermic, yes, and benzene reacts less readily, bromine reacts with benzene less readily than with cyclohexene. All three do, so the answer is A. So which statements are correct about recrystallization? One is correct and two is correct. However, three, that is incorrect, and so your answer for 14 is B. And finally, question 15, which of the following could react with a compound below to form a carbon-carbon bond? Well, one would, because that would put a methyl group on the benzene ring. KCN in ethanol would, because the CN would replace the BR. And methanol and sulfuric acid would not. That would be an esterification reaction, and so that would form a carbon oxygen bond like so. So 1 and 2, so your answer is B. So we now move on to section B. And first of all, we need to name this molecule here. So if we take a look at it, you can see that our longest chain is got 1, 2, 3, 4. So that's butane. Coming off the second carbon is our alcohol group. So butane 2O, and then this is a methyl group coming off carbon number 3. So 3-methyl butane 2O. So I pop the structural formula of alcohol A there. If I heat this alcohol with an acid catalyst, I remove the H from one carbon and the OH here. So I could remove the H from that to produce this alkene here, or I could remove the H there to produce this alkene there. Okay, so I'm now going to heat the alcohol with sodium chloride and sulfuric acid. So that generates HCl. So I pop that in the equation. And I replace the OH with a Cl to make a halogenoalkane, and I'll make H2O as the other product. So this is a bit of a cheeky question here. Notice you have got 3 alcohol groups here. This one is a primary, this is a secondary, and this is tertiary. Those tertiary will not be oxidized. Secondaries go to ketones, which I've done here, and primary goes to carboxylic acid there. So I've got 3O there to make all the oxidations happen, and I also make 2H2O. So I now start with compound C, and I am going to add methanol in sulfuric acid. So that of course is an esterification reaction. So I produce 2 ester groups on the end of the carbon chain. If I react with steam and phosphoric acid, I put I add water across the double bond, which I have done here. And if I polymerize that, that is going to be addition polymerization, because I've got a nice alkene group there, double bond. So you just draw it as an H shape, which I've done here, and polymerize it. So I'm now going to draw in 3D this alpha amino acid. The easiest way to do it is to draw it like this, and then just swap these two groups around like so. So you make sure that you get both optical isomers there. Makes it nice and easy for the examiner to spot quickly as well. And then I'm looking at lysine, and I'm reacting this with dilute hydrochloric acid to form a salt. Notice that the R group also contains an NH2 group, so you will put a proton onto both the nitrogens here and here, and to produce two NH3 groups plus. So this is a little bit of a cheeky one, but it's not too bad. Remember, when you hydrolyze a protein, you will break all the amide bonds. So I've marked on the molecule there the bonds that will break in red. So you just copy it out, and on the end of here will produce a carboxylate salt, and the same would be produced here, as I've shown down here. I've also shown you will produce ammonia here from this one going off. They didn't want it because they didn't want to do organic products, but I've shown it anyway. Don't forget, because you're in sodium hydroxide, you produce the carboxylate salts, not the carboxylic acids. Okay, so I have got three isomers, two nitrophenol, three nitrophenol, and four nitrophenol. Can carbon NMR spectroscopy be used to be distinguished between them? Well, let's have a look. Two nitrophenol, I have got 6 different types of carbon. All of these 6 carbons on the benzene ring are all in unique environments, so I would see 6 peaks. Again here, I would see 6 peaks. There's no symmetry, planes of symmetry in that molecule, so I see 6 carbon environments. However, for 4 nitrophenol, I would see 1. These 2 would be the same. These would be the same, and that one would be on its own. So I would see 4 peaks for 4 nitrophenol. So he's partially correct. So he would see 6 peaks for 2 nitrophenol, 3 nitrophenol, and 4 peaks for 4 nitrophenol. So 4 nitrophenol can be distinguished, but 2 and 3 cannot be distinguished. So why does phenol react more readily than benzene? Well, key things. The oxygen atom has a lone pair of electrons. This lone pair of electrons can be donated into the benzene ring. This increases the electron density of the benzene ring and makes phenol more susceptible to electrophilic attack. Okay, so you've probably not seen this reaction before, but you can complete it knowing what you know about benzene chemistry. So this is, of course, electrophilic substitution that we are doing. So the first step is that the electrons come out of the benzene ring, as I have shown here, to attack the sulfur, which is delta positive. You know this bond has got to break because it's shown it as being broken there. So there's your intermediate, which I've drawn here, and the final step is your carbon-hydrogen bond here breaks. The 2 electrons go into the benzene ring and you produce H+, which they've shown you there. So question 19, this goes back to AS chemistry, doesn't it? So we're looking at halogenoalkanes and the rate of hydrolysis. So how does the halogen in the haloalkane affect hydrolysis? Well, the smaller the halogen, the slower the hydrolysis, because the stronger the carbon-halogen bond. So CF bond is hydrolyzed the slowest, then the CCl, then the CBr, and then the CI is hydrolyzed the fastest. And that's because the carbon halogen bond is increasing in length as you go down the group, which makes it weaker and more easily to break. And then we've got a nice nucleophilic substitution reaction here. Probably what freaks you out a little bit is that it's chlorocyclohexane, but you know, it shouldn't be quite straightforward. You're just replacing the Cl with the OH, so you would have seen this many times before, but probably just without the ring attached, and maybe not in skeletal formulae, but it shouldn't matter too much. Don't forget your dipole. In comes the OH minus, like so. The carbon chlorine bond breaks to give you your product and Cl minus, like so. So you now need to do a quick diagram. It doesn't have to be fabulous, but you've got to have the main things. You've got to show that you are heating the container up. You've got a round bottom flask. You've got your condenser and you've got water going in the bottom and water coming out the top. And please do not seal it at the top. It's got to be open because otherwise it will explode. So now we've got to identify E, F, and G. So they told us that the organic product F has a molar mass of 74, and when you add excess silver nitrate, you form 1.88 grams of precipitate G. And you know that you will have that will be equal to 0.01 mole because of precipitate G, because that's the number of moles of haloalkane you started with. So from that you can find your molar mass of X by putting the mass of the precipitate over the number of moles of the precipitate to get 188. If you take 107.9, which is the relative atomic mass of silver, away from that, you get 80.1, and that means that your halogen must be Br, and therefore precipitate G is AgBr. Right, so you now know you've got Br, so you know your precipitate was AgBr. Okay, so your organic product F has a molar mass of 74, and it also has a chiral carbon. So you know organic product F is an alcohol because you've refluxed your haloalkane with excess sodium hydroxide, which makes an alcohol. So you take your 74 and you minus 17, which is the molar mass of OH, and you get 57. And 57 comes to C4H9. And then it's a matter of playing around. So if you've got 4 carbons, you need a chiral carbon in there. So there's your chiral carbon there. You've got your OH group attached, you've got an H, and then you have a methyl and an ethyl group, and that will give you your chiral carbon. And therefore the corresponding haloalkane E is shown in blue there. Okay, so we need to explain why we have the E isomer. Okay, so you're looking for higher priority groups. So basically, if you compare these two groups here, this is going to be the higher priority group because although you start with a carbon initially there, the next atom along on this one will be a hydrogen, but on this one is an oxygen, and oxygen has a higher atomic number than hydrogen. And then this side, obviously carbon is going to have a higher priority than hydrogen. It's got a higher relative atomic, it's got a higher atomic number, and therefore your two highest priority groups are opposite each other, and therefore it is the E isomer. Right, so nice little one here. How do we test for an unsaturated carbon chain? Well, this is GCSE, isn't it? So you add bromine and it will go colourless. How do you test for an aldehyde group? Well, this one we use Tollens reagent and you will see a silver mirror. And describe a chemical test to confirm that they both contain a carbonyl group. And how could the products of this test be used to distinguish them? We cannot use spectroscopy. So for this one we will add 2,4-dinitrophenylhydrazine and we would see a yellow precipitate. That would confirm that they contain a carbonyl group. How do we then identify the products? Well, we would take the melting point of the crystals of the orange precipitate and then we compare that to known values in a data book, and that would tell us which of the two compounds we have. Okay, so another page where we have to fill in the compounds. So this is all from synthetic roots. So first of all, let's have a look at this one. We are add in sodium borohydride, so that will reduce my aldehyde group to a primary alcohol, which I've shown there. Here I've added a CN, I've got a hydroxynitrile group here, so for that you add HCN. You could have said potassium cyanide and sulfuric acid, doesn't matter. Going from here to here, you are adding H+, that hydrolyzes the nitrile to give you a carboxylic acid, like so. And then excess H2 and nickel will add hydrogen across your carbon-carbon double bond and also across your nitrile group, like so. Right, okay, so this is electrophilic addition, as it tells you here, and we're going to add ICl across that double bond. So you look at your electronegativity values there, and you will see that chlorine is more electronegative than iodine. So your dipole is going to be as I've shown it there, which means the iodine will approach the double bond. Right, so that's the first thing you need to think about. The next thing is how will that add across the double bond? And as you'll know that the more carbons you have attached to a carbon, the more stable the carbocation here will be. So if you imagine this was HCl approaching, you would know the rule that hydrogen attaches to the carbon with the most hydrogens already attached. So you can use the same rule here, apart from it will be iodine will attach to the carbon with the most hydrogens attached, and that of course is this one here. And that produces your carbocation here, which is a tertiary carbocation. If it had been the other way round, you would have put your carbocation there, which would have been a secondary carbocation and not so stable. Then in comes your Cl minus to add there to give you your major product, like so. So in addition to the major product that I've shown, you would also make the minor product. So the minor product is going to be C6H5, and then you're going to have your Cl attached there, and then here you would have your iodine attached, and then your aldehyde, like so. So that would be your minor product. Right, so more synthetic routes. So I'm starting with this compound here. So let's have a look. I've got a phenol group there, and I've got a carboxylic acid there. So first of all, I'm adding sodium carbonate. That won't touch the phenol group, but it will react with your carboxylic acid. Sodium hydroxide will deprotonate both, as I've shown up there. And bromine, of course, will undergo electrophilic substitution and add onto your benzene ring there. I've put the bromine there. It doesn't matter, you can put it anywhere. You can have multiple substitution if you like as well. Okay, now I've got to get compound H to an acyl chloride. So acyl chloride is where you replace that OH with a Cl, which I've done there. And for that you need SOCl2. And then you are going to make a polymer. So the polymer will be a polyester. You've got, what you could consider to be an alcohol group there. I know it's a phenol, but phenols will react with acyl chlorides, so it reacts to give you your polymer I, like so. So you've got a gas chromatogram there, and also some mass spec spectrometry data. It gives me the concentration of ester K in the product, and I need to find the concentration of ester M in moles per decimeter cubed. So first thing, I know the molar mass of K is 166, so I can find the concentrations in moles per decimeter cubed, which I've done there. And then it's just a matter of using your relative intensities to scale that up. So M is 5.9, K is 4.3. So if you times by 5.9 over 4.3, you get 7.5 times 10 to the minus 4 moles per decimeter cubed. Okay, so you now need to deduce possible structures for J, L, and M. So J has a mass of 152, and L and M have 180. So you'd need to draw the whole of the molecule out. I've just put the R group in. So for J, it's going to be OCH3, like so, and you can follow on. How did I get that? Well, I know that it comes to 152. You take away all of this part of the molecule and you're left with 15, so you know it's going to be CH3. For the other two, they're both 180, you're left with 43, so it's got to be a propyl group, and there are two ways of doing that, which I've shown there. Doesn't matter which way you do these two, either way is fine. Okay, so incomplete combustion of heptane I've shown. Remember, you produce carbon monoxide rather than carbon dioxide for incomplete combustion. And then you need to explain the boiling points. So let's take pentan 1-ol first of all. Pentan 1-ol has a much higher boiling point than the other two. Why is that? Well, because pentan 1-ol has hydrogen bonds that are stronger than the London forces that act between hexane and heptane molecules. And therefore they require more energy to break. Now let's consider heptane and hexane. Heptane has a longer chain, therefore has more electrons than hexane, so it has more surface contact and therefore will have stronger London forces than hexane, and therefore it will take more energy to separate heptane molecules than it will hexane molecules. Okay, so a slightly odd one this. So I completely combust compound N, and I produce 2.97 grams of carbon dioxide and 1.62 grams of water, and they tell me the molar mass is 76. So the first thing I could do is work out the moles of carbon dioxide and the moles of water. The moles of carbon dioxide will be the same as the number of moles of carbon that were in the molecule. However, the moles of water, to find the moles of hydrogen atoms in the molecule, you have to double it to 0.18, because in every one water molecule there are two hydrogen atoms. So once you've done that, you can find your ratio to carbon and hydrogen, which is 1 to 8. Once you've done that, if you add those up and find out what you're left with 32, which will be your two oxygens. Therefore, your formula is C3H8O2. So you can put it in any structure you like. It doesn't really matter. That's one example. Okay, so carrying on then. This molecule looks pretty awful. So how on earth would you make it from propane, 1,2,3 triol, and a carbonyl compound? Right, okay, so here, as I've drawn, that would have been, you've got your O there, your O there, and O there, your propan 1,2,3 triol. So what are you left over with? Well, you're left over with this part here, which must have been your carbonyl compound. So it looks, when you add it together, you have got yourself propanone as the other molecule, and you will make water as well. Okay, and now we need to work out a structure. So we've got an NMR, elemental analysis, and mass spectrum. Okay, so let's go for it. So if I find the empirical formula, first of all using my elemental analysis, I get C2H4O. I then need to scale that up for your molecular ion peak to C6H12O3. Right, so they give me a bit of a clue down here. They've told me that when I run it in D2O, two additional peaks, well, without D2O, there are two additional peaks with the same relative peak areas, one at 11 ppm and one at 3.6 ppm. So that suggests you've got a carboxylic acid and you have got an alcohol group. Right, and now we need to look at your NMR here. So you've got your peak here, which suggests you've got an oxygen and then a CH, so it's this H here which is appearing. It's intensity 1, so you've only got one of them, and it must be next to, it's a quartet there, so it must be next to a CH3 group. So let's track, if you look, we tracked that CH3 group to here, where you've got a peak of intensity 2, which is a doublet, and it's a doublet because of it having one neighbour there. So that's a bog standard CH3 group. And then finally, you've got this group here, this peak of intensity 6, no splitting, so it must be two methyl groups attached to a carbon like so, and that carbon here cannot have any hydrogens on it because there is no splitting. Then you need to just pop it together. So you can do this in various ways, and I can show. So what I've done is, this is your group that we had here, your CH3 next to a CH. Then next to that you can have this group here, which we found to have. And then on your bits you're missing, you can put your carboxylic acid on the end there and your OH there, like so. Remember, hydrogens on oxygens do not split, so that would mean why that hydrogen is not split by this one here. It's only split by these hydrogens there into the quartet. Right, and that is that paper wrapped up.